Improvements to Pierce County's Lahar warning system are in the works to help warn people earlier in the event of a volcanic eruption at Mount Rainier.
Well, it was definitely the talk of social media on Wednesday morning. Some panic over Mount Rainier.
Mount Rainier's current seismic behavior has drawn significant scientific attention, especially following a surge of unusual earthquakes that began in April 2025. These seismic events were not the kind typically attributed to shallow tectonic shifts or glacial movements. Instead, they occurred at greater depths and exhibited patterns and waveforms that hinted at processes deep within the Earth's crust. Such characteristics strongly suggest that the volcano may be undergoing internal changes potentially related to magma recharge or hydrothermal disturbances. This activity is concerning due to Mount Rainier's geological history, topographical profile, and the dense population living within its extended hazard zone. The location and depth of these recent quakes, particularly between 5 to 14 kilometers beneath the surface, make them scientifically significant. At these depths, typical surface-related events such as ice cracking or rockfall are ruled out. These seismic anomalies occurred in tightly clustered swarms, with many exhibiting unique long-period waveforms, a sign often interpreted as the movement of magma, volcanic gases, or superheated water. Some of the most compelling evidence for subsurface fluid dynamics comes from the detection of earthquake multiplets. These are small seismic tremors that repeat with near-identical seismic signatures, indicating a consistent source, likely a structural or pressure-based phenomenon. In some cases, these multiplets occurred in rhythmic bursts, suggesting a regular non-random triggering process. The implications of these patterns are profound. Multiplets and harmonic overtones, as detected during this period, typically emerge when fluid moves through tight fractures or when magma or steam accumulates in pressurized chambers. In Mount Rainier's case, these patterns, combined with the observed lateral migration of seismic events, imply that something is shifting underground, potentially the inflow of magma into a pre-existing chamber or the opening of new pathways through which fluids travel. These signs indicate dynamic changes in the volcano's internal plumbing system, which is worrisome for geologists and emergency managers alike. Mount Rainier is classified as a stratovolcano, a type characterized by steep flanks and a composition built from alternating layers of hardened lava, ash, and pyroclastic material. It towers over 14,400 feet and contains more glacial ice than any other peak in the lower 48 United States. This abundance of ice contributes not only to its iconic beauty, but also to its immense potential danger. The primary hazard posed by Mount Rainier is not lava, but lahars, volcanic mudflows that can be triggered when an eruption, a structural collapse, or even intense heat causes rapid glacier melt. These mudflows behave like flowing concrete, capable of obliterating everything in their path and traveling tens of miles down river valleys. Communities situated near the Puyallup, Carbon, and Nisqually river systems are particularly vulnerable. Towns such as Orting, Puyallup, Sumner, and portions of Tacoma fall within the extended hazard zone. The proximity of such a large population to a high-risk volcanic region makes Mount Rainier uniquely dangerous, not because it erupts frequently, but because even a moderate event could unleash catastrophic consequences. More than 3 million people reside within the area that could be impacted by lahars, emphasizing the urgency behind monitoring efforts and disaster preparedness. In response to the recent seismic changes, the U.S. Geological Survey (USGS) and the Pacific Northwest Seismic Network (PNSN) have significantly increased their monitoring activities. This includes deploying additional portable seismometers around the volcano's western flank, thereby enhancing the accuracy of event location and waveform interpretation. These instruments complement existing permanent stations and contribute to a more detailed understanding of the volcano's internal state. GPS stations in the area are also being carefully analyzed for signs of ground deformation, such as uplift or tilt, which might indicate magma movement or fluid buildup. Analysts are examining both vertical and horizontal components of GPS motion to identify even the smallest anomalies in the crust. Thermal surveillance has become another vital aspect of the monitoring effort. Using both satellite-based and drone-mounted thermal cameras, scientists are searching for small-scale temperature increases that could reflect changes in hydrothermal activity or early magma ascent. These tools can detect temperature variations of less than 1 degree Celsius, making them incredibly sensitive to minor environmental changes. The presence of new heat sources or increased steam emissions could be an early indicator of volcanic awakening. Gas monitoring also plays a central role in evaluating volcanic unrest. Sensors near Mount Rainier's summit vents measure gases like carbon dioxide, CO2, and sulfur dioxide, SO2, both of which are typically released as magma rises and depressurizes. Scientists are paying close attention to fluctuations in the CO2/SO2 ratio, a diagnostic marker of magma depth and saturation. A change in this ratio could provide crucial clues about whether magma is ascending closer to the surface. Thus far, gas emissions have remained within expected limits, but real real-time monitoring continues. To process the growing influx of data, machine learning algorithms have been implemented to analyze seismic recordings in real time. This technology has proven effective at identifying patterns that human analysts might overlook, including low-amplitude multiplets and subtle waveform anomalies. The insights derived from this automated analysis are helping scientists develop more accurate models of subsurface behavior. The integration of artificial intelligence into volcano monitoring marks a significant advancement, offering faster and more reliable detection of potentially hazardous developments. Mount Rainier's volcanic system is particularly complex due to its combination of glacial coverage, steep terrain, and active hydrothermal and magmatic components. While the mountain has not erupted magmatically in over 1,000 years, dormancy does not equate to extinction. Ongoing thermal emissions, persistent seismicity, and gas release confirm that the volcano remains alive. As such, it is ranked among the most dangerous volcanoes in North America, not for its frequency of eruptions, but for the scale of impact an eruption could produce. The three leading theories regarding the current seismic activity are interconnected and not mutually exclusive. First, the possibility of magma recharge suggests that molten rock is slowly ascending from the mantle into a mid-crustal reservoir. This process can generate pressure, trigger rock fracturing, and initiate seismic events, all without necessarily leading to an eruption. Second, disturbances in the hydrothermal system beneath the summit could account for many of the observed earthquakes. As superheated water and gases circulate through fractured rock, changes in pressure or permeability can cause tremor swarms, multiplets, and low-frequency quakes. Finally, tectonic stress redistribution could be a factor, as movements along regional faults or shifts in nearby volcanic systems might be transferring strain to Mount Rainier's internal structures. Any of these processes, alone or in combination, could indicate that Mount Rainier is transitioning into a more active phase. Whether this ultimately leads to an eruption or represents a cycle of internal adjustment is unknown. However, the current activity demands vigilance. It underscores the necessity of ongoing research, public education, and robust emergency planning. One of the greatest challenges in volcano science is distinguishing between benign unrest and precursors to eruption. Often, only hindsight reveals which signals were warnings and which were merely background noise. For communities living within Mount Rainier's shadow, this uncertainty necessitates preparation. Improvements to lahar warning systems are underway in Pierce County, aiming to give residents earlier alerts in the event of volcanic activity. These efforts include siren systems, automated alerts, and education programs designed to help people understand the risks and know how to respond. Given the speed at which lahars can move, potentially reaching populated areas in under an hour, early warning is essential to saving lives. Scientists also emphasize the importance of community resilience. This involves not only infrastructure improvements and escape planning, but also fostering a culture of awareness. Public understanding of volcanic hazards can reduce panic and improve response times during emergencies. Media coverage plays a crucial role in this, though it can sometimes misrepresent events. For instance, earlier this year, a cloud formation above Mount Rainier was mistaken for volcanic venting, sparking social media panic before authorities clarified the situation. While the incident turned out to be benign, it highlighted the need for accurate communication and public trust in scientific institutions. The interplay between natural beauty and hidden danger defines Mount Rainier. It is a majestic symbol of the Pacific Northwest, attracting hikers, photographers, and geologists alike. Its glaciers shimmer under the sun, and its silhouette dominates the skyline. Yet beneath this tranquil exterior lies a dynamic, volatile system capable of dramatic and destructive change. Understanding this duality is key to appreciating both the wonder and the risk the mountain represents. Ongoing research seeks to refine models of Rainier's internal processes. This includes mapping subsurface structures using seismic tomography, analyzing gas chemistry trends over time, and developing better simulations of lahar flow scenarios. These scientific endeavors are supported by collaborations between academic institutions, government agencies, and local authorities. The integration of geological data, satellite imagery, and real-time telemetry forms a layered defense system against unexpected eruptions or collapses. Scientists are particularly interested in the role of resonance phenomena in the mountain's behavior. If certain multiplets are caused by vibrating fluid-filled cavities, they may serve as indicators of pressure buildup or structural weakness. The repetitive nature of these events, along with their harmonic qualities, provides a unique window into subsurface dynamics. When paired with thermal and chemical data, this seismic information allows for more comprehensive risk assessment. Ultimately, the goal of all this monitoring is not merely scientific curiosity, but public safety. By detecting changes early, authorities can mobilize resources, evacuate at-risk areas, and potentially mitigate the worst outcomes of volcanic unrest. Mount Rainier's power is undeniable, but so too is the capacity of modern science to observe and understand its signals. With continued vigilance, collaboration, and innovation, it is possible to coexist with this formidable natural feature. As the April and May 2025 seismic events fade from immediate news cycles, the mountain remains under close observation. New data continue to be collected, and researchers remain alert to any deviations from expected patterns. The story of Mount Rainier is far from over. Its slopes may be still for now, but the signs beneath suggest a system that is far from static. What lies ahead depends on countless variables, but thanks to relentless monitoring and ever-advancing technology, we are more prepared than ever to meet whatever challenges the volcano may present.